Okay, good afternoon, and thank you for staying on for the closing session. As the session says, we are now nearing the end of the conference. There is a slight change in the program. We will start with the awards, then the lecture by Professor Reklaitis, then the presentations by the two future conferences, and then we finish. And then there will be coffee, tea in the foyer, not in Hall A. So the program is, we will give the poster awards, then the EFCE award, and then the Roger Sargent Medal. Then, as I said, Professor Reklaitis will talk about highlights and new directions for PSE, and the two future conference presentations, ESCAPE26 and PSE 2018. So we will start with the poster awards, and this will be 3 awards for the best posters on Monday, Tuesday, and Wednesday. And these were selected by the panel that was mentioned in the technical program. So I thank all the panel members. They did a great job looking through almost 100 posters every afternoon and coming up with their selections. So the first winner, I hope the winners are here, is Torben Egger and George Fig. The paper is Modeling and Simulation of an Enzymatic Catalyzed Reactive Dividing Wall Column, poster P126. Any of the authors here present? Okay. But we will send this to them. There is one other advantage that they will get, but I will tell you for the next winner. And I'm sure the next winner is here. This is, now I don't know whether it's Imperial College or Texas A&M, but it's Amit Jubeda and Stratos Pistikopoulos. Please, if one or all of you are here. Okay.
It's good to get an award regardless destination. So.
The certificates are for all 3 authors, and now I will tell you the secret. I made a deal with ESCAPE25 that one of the authors will get a 50% discount.
Okay. Not me, not me.
And the third winner, I think I had seen him in the last keynote session, so I hope he's here, is the paper from Canada. Noor Haroon, David Tucker, Thomas Adams II. So,
thanks.
And one of you also will get 50% discount at ESCAPE26. Yeah. Okay, so now we come to the next award winner, and this is the EFCE Lifetime Achievement Award. And I would like my colleague, Jean-Marc Leland, he's the scientific vice president. He will make the announcement.
So, ladies and gentlemen, dear colleagues, it's a great pleasure and an honor to me to ask Professor Reklaitis to come there. And under the behalf of EFCE, I am the honor to give you the 2015 EFC Lifetime Achievement Awards in recognition of the role you play for more than 40 years as representative of the Czech and Hungarian EFC member societies, as an active member and a chairman and new refreshed chairman from the CAPE Working Party from EFCE. And also these awards, it's acknowledge all the substantial service to chemical engineering education and qualification, and also to your research achievement and very heavy contribution to the organization of numerous meetings, workshops, and courses related to CAPE, related to process integration and modeling, related to sustainability, including the famous ESCAPE and press series events. So, Jerry, it's a very great pleasure that Professor Gani and myself.
That's the award. You can give the name. Okay. So, congratulations.
Thank you very much indeed. I deeply appreciate the award from European Federation of Chemical Engineering. As Professor Gani said and Professor Lanan, I've been around quite a long time. You know, it doesn't look so, but if I remember pre-ESCAPE conferences, ESCAPE conferences. Well, ESCAPE conference is 25 years old, which is, as I said at the opening, the best age. I'm a little bit older, but still ready to do whatever I can for European Federation of Chemical Engineering and for the Working Party, CAPE Working Party, Process Intensification Working Party, and also for sustainability. Thank you very much indeed.
Thank you. And the last award to be given now is the Roger Sargent Medal. This is awarded to one or more individuals who have made a significant recent contribution to the research into computer-aided product and process engineering. The contribution could encompass, but need not be limited to, a concept that has promoted much interest, the solution of an unsolved problem, new methods, tools leading to innovative processes, products, or a significant advance of the state of the art within the process systems engineering. The Sargent Medal is initiated by IChemE of UK, and a panel of members were selected as the selection committee to decide about the award. The process was an open nomination, and based on the nomination, the panel members decided. I would like the panel members who are here to also come, please. And there is one panel member who was at the conference, but he had to go back. That is Professor Mannan from Malaysia. And we all unanimously agreed that Professor Ignacio Grossman from Carnegie Mellon University is the first winner of the Roger Sargent Medal. Please, Ignacio. And there is a nice certificate from the IChemE and a real medal also made by the IChemE. Thank you very much. Please.
All right. Really, thank you so much first to the Institute of Chemical Engineers for this great distinction. It is truly a great distinction and an honor for me to be the recipient of this Roger Sargent Medal. And the main reason is because of the great admiration and respect I do have for Professor Roger Sargent. As you all know, Professor Sargent can really be considered to be the founder of the area of process systems engineering. In fact, he has been the intellectual leader of the area. He's the one who has provided, if you wish, a strong foundation, especially mathematical foundation, to process systems engineering. In fact, I think we could also say that one of the reasons we're celebrating this PSE and ESCAPE meeting is because of him, because he's the one who really has founded the area. He has obviously made tremendous contributions, and one of the examples to see the kind of contribution he has made is if you look at his academic tree. Many of you, I'm sure, know about the academic Sargent tree, and I thought it would be interesting to try to estimate how many of the participants at this meeting belong to the academic Sargent tree. I couldn't quite come with a number, but I could come up with some lower and upper bounds. So my estimate, the lower bound is 20%, the upper bound is 40%. But needless to say, the tremendous has been absolutely tremendous. And I have been really, truly fortunate to have had Professor Sargent also as a mentor. He was my advisor. He was the one who really inspired me to, work in this area and set very high standards of quality and innovation. So I'm really most grateful to be with again to Professor Sargent. I'd also like to take the opportunity here to thank first my graduate students. I think one of the reasons I'm here is of course because of all the hard work that my graduate students have made and the excellent contributions that they have made in the area. I'm also very grateful to many of the collaborators that I've had throughout the world with whom we have shared, research experiences. I'm also very grateful to my colleagues at Carnegie Mellon who have provided a very stimulating environment. Also very thankful to the process systems community at large. I really thank the friendship, the support that I have received from all of you. But I also have to thank very much my wife, Blanca. I think if I'm here, it's really because of her. Without her, I would simply not be receiving this award. So again, in closing, needless to say, this award, of course, means a lot to me. I was extremely thrilled when I found out that I was made the recipient of this award. And again, I would like to thank very much the IChemE. I would like to thank very much the committee for receiving this award, because I could also say that perhaps this is the most important award that I have received in my academic career. Thank you. Thank you.
And this. Okay, so before I go to the next event, I just remembered that I forgot to mention that all these nice certificates are made by Elsevier because the poster sessions were sponsored by Elsevier. Please. So next we move on to the final lecture of this conference, except for the two presentations afterwards. This lecture is going to be given by Professor Reklaitis, and Rex is Burton and Catherine Gage, Distinguished Professor of Chemical Engineering at Purdue University and Deputy Director of the NSF Engineering Research Center on Structured Organic Particulate Systems. At Purdue, he has served as the head of School of Chemical Engineering and director of the Computer Integrated Process Operations Center. His expertise lies in process systems engineering, the application of information and computing technologies to process and product design, process operations, supply and supply chain management, current research. I think all of you know Rex very well, so I will not read out all these things, but he's a member of the U.S. National Academy of Engineering, a fellow of AICHE, and past editor-in-chief of Computers and Chemical Engineering. He has received a lot of awards. I will not list them now. He has served on the board of directors of AICHE, the Council of Chemical Research, and the Cash Corporation. He has published over 200 papers and book chapters and authored 8 books. I would invite Rex to give his talk on highlights and new directions for PSE.
Thank you. So thank you very much for the introduction and for the opportunity to chase everyone off the conference site. As Rafiq pointed out, I'm supposed to have a dual assignment, is to first highlight some of the things that you heard or should have heard if you had been able to attend all the sessions, and then secondly to draw on your collective wisdom to try to focus on what are, based on our current directions, what are really exciting new things for us to look at in the future. So that's the objective, and so my outline is really very straightforward. I will briefly touch on PSE and its traditional scope, then taking that as a template, try to map what was the scope of what we experienced this week and how does that match with that traditional scope, how does it enhance it. Then I would like to point out some areas of special interest, focusing on specific papers. And finally, say the new directions part. So that's the agenda. And just to start it off, I thought I would borrow from a definition of process systems engineering that George Stephanopoulos cooked up some years ago, which is pretty concise. And it says it's the engineering of systems involving physical, chemical, and biological processing operations, where the key words really are engineering and systems, and of course, the processing as well, because that really is the domain within which we apply our systems engineering concepts. Now, excuse me, the traditional processing systems that our community has focused on in over 50 years have included, of course, chemicals and materials for society's wants, fuels and energy from fossil and non-fossil sources, quality of water in the environment, diagnostics and therapies for treatment of disease, and of course consumer goods to enhance quality of life. Now, given this broad categorization of sort of things we've worked at over the past 50 years, what has happened? What have we talked about at this conference? I've put together a couple of shopping lists, and I won't read all of them to you, but they indeed do cover the range of topics that we've talked about. It certainly both includes things that have been treated in the past few years, but also I view as kind of a renaissance of process engineering. We've really covered such a broad spectrum of processing operations, and particularly I think in this meeting, this broad spectrum was particularly notable because it was pursued by all 3 geographic areas where PSE is practiced. Lots of contributions from Asia, lots of contributions from the Americas, and substantial contributions from Europe as well. And of course, some of these areas have more recent focus. Certainly the biomass arena as a source for chemicals is really a topic of the last few years. Carbon capture is a topic of the last few years. The notion of actually doing something with CO2 other than stuffing it into the ground is a relatively new focus for our community. Renewable energy systems in general, actually a few years ago, it would have been inconceivable that the chemical engineers could have, courageously marched into telling the world how to handle electric power systems, but we're doing that with great vigor. Certainly, those of you that attended the keynote session just a little while ago saw some interesting presentations in looking at human physiology and treatment of disease in general. The notion of pharmaceutical engineering or pharmaceutical products and processes, we've looked at that over the years, but I thought at this conference in particular, there was a significant increase in activity in this domain. Shale, of course, isn't just a U.S. phenomena. It's a phenomena that's arising across the world and has led to some really interesting applications for our community. So we've covered the traditional terrain, and there's a whole new field of activity that our community has now been practicing, and that's really wonderful to see in this conference. The PSE community has also had significant impact over its life, and certainly if you think of the tools, the product of our research that have actually had industrial impact, certainly flow sheeting systems are there, model predictive control is there, dynamic systems modeling, process integration and synthesis in general, and process planning and scheduling, to say nothing about real-time process optimization. So those have been areas where we can actually point to delivering value to the industry. It isn't just academic pursuits. So if we look at this accomplishment list, we can then go to what has transpired at this conference. And certainly, if you do, keyword, you'll find we've had plenty of discussion of product design, of process synthesis, of energy integration, of sustainability and life cycle analysis, which are relatively new sort of objectives for our community. Design under uncertainty was, in fact, the subject of the lead plenary of this conference. On the dynamics and control side, certainly control theory, plant-wide control, monitoring, estimation were covered, and then control of some specific families of unit operations, columns, batch operations, crystallization control. Among those, I would say that the area that has particularly seen emphasis at this meeting has been that of product design. Product design has not been a new topic for us. It's something that we've been pursuing for 20 years, but I was struck by the fact that at this meeting we really had quite a concentration. In fact, those of you that attended FOCAB-D a year or so ago, that concentration was much smaller. Here we had a very interesting plenary presented by Professor Ka-Eng. We've had at least 7 keynotes and some 30 individual contributions. Most of those contributions still pursued this sort of sequential approach to product design, which started off with identifying in various ways candidates for products, then selecting from those candidates, then conducting the process design activity, repeating that with the candidate list, and then choosing the best. However, in addition to that, I thought a really important contribution that emerged at this conference is really the beginnings of tools, that the user community can use, because we need these kinds of tools. Envision doing process engineering without flow sheeting packages. It really wouldn't have advanced very well. So we do need tools in addition to new concepts, and I thought there were at least several presentations of tools. Now, admittedly, the principal contributions were looking at blended products, but I think we've got some interesting work in terms of learnings on how to use molecular modeling tools to really help advance this domain. Of course, the target is really that of integrated product and process design, and one would hope that we would be able to systematically replace the sequential process with a simultaneous one. But there already are papers here and there which begin to do this simultaneous product and process design. So lots of good contributions here. Clearly a key area for PSE research going into the future. Now, if we look at additional sort of topics of scope here, certainly in the operations domain, if you look across the program of 500 papers, we've covered plant complex management. We've covered supply chain, planning, scheduling, intelligent systems. No one talked about dumb systems. We did talk about abnormal events. I guess normal events are not of interest either. And we did have some discussion of process safety. Integration was very much a topic. Indeed, a very nice presentation by Professor Epistokopoulos addressing, some aspects of design control integration, but also integrating from the supply chain down to the process unit, and of course this issue of product process design. On the tool side, we've covered significant advances in basically mathematical programming and optimization. Again, optimization of uncertainty, integration of CFD and population balances, estimation problems, of course, modeling and simulation in general. As you recall from the opening presentation from Professor Ghani, modeling and simulation is the largest sector among the contributions for the conference. And we had agent-based framework and some things under the category of cyber infrastructure, which were principally, I would say, some both data management and sort of advanced computer architecture applications. Now, the area that I found particularly interesting as a theme, which emerged more strongly at this conference, is that of really looking at supply chain as not a monolithic entity controlled by one central player, but the notion that there are really multiple interacting entities that drive a supply chain. And again, this is a topic that has emerged in prior meetings, but I thought it was notable at this conference that we really had a number of interesting contributions in this area. And one of them used the now well-established tool of agent-based model to really look at a fairly complicated supply chain. And that was a presentation that some of you may have heard on agent-based model of the German biodiesel supply chain, which when you look at the chart there basically has a number of agents in it, both farmers and process operations unit, distribution systems, the customers, and of course the governmental agencies that regulate the various transfers that occur. But there are other presentations that really use sort of game theoretic concepts. I thought it was kind of fitting that's one of the contributors used the Nash pricing model, and unfortunately Dr. Nash passed away recently, but I thought it was fitting that someone had a very timely recognition of his impact on our community. But similarly, there are several other presentations that really dealt with the interaction between at least two entities, and either in terms of determining transfer prices or in terms of dealing with sharing of capacities. So I think this is really a very exciting area for the supply chain part of our community, and I hope that it continues to grow because it gets us a little bit closer to reality in terms of how companies currently have to operate. Now, there's a cast of characters that I want to introduce to you because the next phase of what I wanted to do is to go beyond sort of general categories, which I just did, to actual identifying individual papers that we thought were novel. And in order to achieve this, since this community contributed about 500 papers, I decided it was appropriate to launch a paper mining project. This is the equivalent of data mining, but it's on papers. And so I was happy to say that I was able to engage three colleagues, Carl Laird and Sultan Naj and Fenke and myself, to actually engage in this paper mining activity. And we used a range of techniques in order to do this. Of course, very sophisticated AI learning tools and innovation discovery methods. And then, of course, also some old traditional methods, which, even reading papers, and listening to presentations. So we were clearly used a collection of skills and tools in order to achieve this. And so we came up with a list of 12 papers. And this was a very scientifically put together list, so it is beyond question. Now, I've divided them into 4 categories. The first is design. One of the papers that you just may have heard earlier in the day today was Philip Lutz's presentation on process intensification, in which he really pulled together some of the essential elements that are involved in process intensification. There was a very nice application paper that was a joint contribution from AkzoNobel and academia that involved purification, really ethanol water purification, which is a classical problem using some interesting technology. And the third was a water resource management application by a team from Plapiqui in Argentina that addressed a really interesting problem, and that is of how to design and manage wetlands as a way of treating water resources. Now, of these 3, we really only have time to talk about one of them, so I just, will summarize for those of you that weren't at the presentation, the contributions in that paper. Basically, it addressed the problem of, purifying an ethanol water mixture created from biosourced material, and to do this in an energy efficient way, recognizing that the conventional sort of 3-column system that's used to get really high purity ethanol is known to be very energy inefficient. And so what they proposed is an innovative divided wall column design, which is interesting because there haven't really been that many applications in extractive distillation. So they really did extractive distillation. They also used vapor recompression and came up with a very interesting system that could also be called a process intensification, because it had really combined in one unit all 3 of those distillations. And by virtue of using vapor recompression and in addition a side reboiler, came up with a very efficient design. In fact, it's quite impressive that they're able to reduce the energy requirements by a substantial amount, from about 2 to 1.2, and that's really very much needed for the bioethanol, to really be a sustainable sort of product of biomass. And I thought this was really, I should say we collectively thought this was a very interesting example of how PSE can really solve practical problems, okay? Now, in the area of control, we really came up with, identified 3 contributions. One of these was the integration of design, control, and scheduling by the team led by our cross-Atlantic collaborator, Professor Pistakopoulos. Not only his main presentation, but there are 3 application papers that appeared in the program in various forms that really use this concept. There was also an interesting contribution. My name is there, but I assure you I had not much to do with it. It's really colleagues at the Polytechnic Institute in Milan that have put this concept together of really combining the design and control of a batch system. The third was the paper, but was given very capably by Professor Skogestad, which very elegantly summarized some systematic approach to plant-wide control. Now again, we really don't have the time for me to walk through all of these. I encourage you on the plane back to, if you haven't read this, read it, and then contact the authors for the full-length paper. But I'll just briefly summarize, borrowing from Professor Pistakopoulos, sort of the main contributions of this work. And I think, again, I like the fact that not only did the research group put together the intellectual ideas but they actually deliver it into a form, which I'm sure he'll freely share with the entire community. All you have to do is send him an email, and he will let you download it from his Dropbox. But it's really an interesting toolkit, which is built around the theme of multi-parametric optimization, which Professor Pistakopoulos has pioneered over the years, but then also includes the capabilities of building rigorous simulation models. And I was really surprised to see GPROMs was used. I thought for sure they would use MATLAB or something like that, you know. Had a toolbox for producing reduced order models, of course the multi-parametric part, and then, you know, linking this together into a potential MPC formulations, and then allowing, I thought a very nice concept of allowing this to be validated against the high fidelity model. So I think this is really a nice body of work, both conceptually and methodology and delivery, hopefully to the community in due course, and I'm sure Texas A&M will distribute it worldwide, no problem at all. Now, third category was that of operations, and again, there are three contributions that our team identified. The first was the duality-based approach to bilevel optimization, which is presented in the context of capacity expansion, but is really an important general concept. As I pointed out earlier, it really helps address some problems in this multi-participant supply chain environment, for example. There was a very nice summary paper by Professor Yu that really addressed the use of mixed integer fractional programming for a series of applications. And third, there was a paper on scenario-based price negotiation using game theory from the group at UPC. Again, I'll just pick one of those to summarize, and that's the contribution from Professor Yu's group. Essentially, the notion of a fractional program is allow one to address problems in which the objective function is really a ratio of rational functions, and it arises naturally. For example, if you're trying to do optimization of a batch process over cycle time, or if you're looking at maximizing return on investment, or, you know, life cycle optimization and so forth. And while the basic idea is really remarkably simple, when convert the ratio into a parameterized function, and then deal with this parameterized function as an approach to optimizing the original objective function. Now, Professor Yu has, of course, addressed this problem for a few years now, but I think what we've discovered is that he's made some significant contributions here. First of all, in convergence conditions that show that you don't have to solve this effectively root finding problem to optimality. You can do it approximately, which saves a lot of computation time, but then also addressing the issue of global optimization. So this is really, again, a piece of work that sort of not only further develops the methodology, but also expands the range of applications. Then we go to the optimization numerics world. And again, one of the really interesting contributions was that from Professor Ageman's group. They really looked at, you know, identifying transition states and using that as a vehicle within global optimization. A really very important contribution in advancing, I think, global optimization. There was a use of GPU units to accelerate computations, the difficult computations involving population balance computations. And then a third contribution, which was really introduced a dynamic method for computing thermodynamic equilibrium process simulation. And this paper actually appeared in as a poster paper. And I'm not sure how many of you managed to find that paper, but I think it's a very neat concept. And so wanted to spend a little bit of time featuring it. So the basic idea is really how to improve the efficiency, reliability, phase and reaction equilibrium computations, which typically are nested within simulations. And so the goal of this work was to really try to improve the reliability of those computations, because the free energy minimization is typically handled as solution of the optimality conditions. So you're converting it to a set of nonlinear equations. The phase equilibrium, likewise, since you're simply equating free energy, you essentially end up nonlinear equation solving, and we all know nonlinear equation solving typically has difficulties with initial values and with convergence. And so the idea that the group proposed is really a pretty old one. At least, it's been around as long as I have. But I thought the application of it is quite nice. And so the idea is to take this equation solving problem with unreliable convergence and turning it into integrating a set of ODEs. And then, of course, the trick is how do you convert those ODEs into something that's reliably solved, and that they did by formulating this appropriately and then making sure that, second law isn't violated and all that sort of stuff. Now, the advantages, as I mentioned, was less sensitivity initial estimate, more reliable solution by taking advantage of efficient integration tools, and also the possibility of really allowing a combination of these calculations, phase and reaction equilibrium, to be carried out. So really a classical method has been used in other settings, applied to a problem that hopefully will have impact in simulation. So having gone through these 12 featured papers, the last phase of what I wanted to do is focus a little bit more on things that we thought needed more attention, and then finish off with some directions for future research. And certainly the one area that keeps requiring attention from our community is that of safety and design for safe operations. It's been talked about in our community for a long time. We have been encouraged to do things in this area, but it seems like the progress has been relatively slow. But at this meeting, there were some 7 papers that addressed various aspects of process safety. For example, there was an interesting contribution from Rio that talked about, incorporating safety in the design of a control system. So how to test the control system for failures and taking preventative action. There was an interesting contribution from our host institution that looked at how to integrate safety considerations in the workflow associated with design. And then there was an interesting presentation given by Professor Srinivasan from IIT that really focused on an aspect of process safety that really, to my mind, hasn't gotten all that much attention in our literature in the past, and that is really the human factors. And I was struck by the fact that Raj was pointing to the fact that many of the major accidents that have occurred have actually been because of human failure. And certainly the recent train wreck outside of Philadelphia was another example of really human failure, the operator simply going too fast. So I think, we had some interesting cases that were presented here. And I think the message here is we're making progress, but we really need to move a lot faster, because safety, it seems to me you can't talk about life cycle and sustainability and not really deal with safety squarely from design through operations. Okay, so that's an area that needs more attention. Another area that needs more attention, and I guess I'm sort of harping on this subject that repeatedly, is we really haven't done enough to really take advantage of advanced computer architectures. And there is no better example than those of you that may have read the history of developments of CPLEX over the years, where yes, since that software has been used, computing has improved, but actually it's the algorithmic improvements, the cuts and the various heuristics that are built into it that really account for most of the improvements in the size of problems we're able to address. So, I mean, that suggests to me we really need to invest more in this area. And there's certainly been at least 3 papers, but that's a relatively small number out of some 500 that address aspects of it. And one of those papers was from the group by Professor Naj, where they really looked at GPUs, but there was another GPU-oriented paper on the program. I won't go into the details. The main point here is that this is an example of a computer architecture that's relatively cheap, and the comparison that was made here was essentially to do, I thought it was an interesting idea. They're comparing the computing power for the same cost of hardware. So not looking at, speed up based in terms of number of processors, but if you spend X number of dollars on computing hardware, what can you achieve by running this operation? And they got some pretty substantial gains, really up to 35, which takes the application which this was intended for and allows it to be moved in the real-time domain. Okay, so the original application was one of really doing nonlinear model predictive control. Okay. So there's lots of opportunities, seems to me, in this area. Certainly, the more we can do in real time, whether it's for control or it's diagnostics or monitoring, computation will help. There's been lots of developments, I'm sure, at all of your universities in using advanced architectures. And really, we have a very minor community that's actually focusing on the algorithm engineering to take advantage of that. Okay. And there are a couple of those apostles in the audience, so I won't embarrass them by asking them to stand up and having you applaud them. But I think it's a very important effort for us. So if we look in the future, definitely integrated approaches to process safety have to be high on the list. Using advanced computing architectures has to be very high on the list. And then there's 3 other topics that I would call your attention to. We've already had discussions just today on process intensification, data and knowledge management, and multi-scale modeling are the other 3 that I would just take a few minutes to describe. The first of these is the intensification topic, and very conveniently, Professor Lutze had a presentation earlier today. So all I really have to point out to you is that intensification has pluses and it has minuses. And the pluses are, of course, the reduction in complexity in terms of the number of distinct equipment items that have to be used. And that in itself offers some gains in safety and cost and so forth. It does have some minuses in that you reduce the degree of freedom and control becomes more complicated. But this is something our control community always applauds because it's not interesting to do control research if control isn't complex. But that's the trade-off. And of course, there have been examples of continued baffled crystallizers and reactors and divided wall columns and so forth. But the challenges there are, again, those of modeling, of dealing with more complex systems. Inherently, there is, of course, intensification, pathway identification required. And of course, the really interesting subject, which Professor Lutze touched on, I guess Dr. Lutze now, if I recall his slide, he's migrated to a company, is really going back to synthesis based on phenomena rather than synthesis based on existing hardware. And I thought there have been several people that have raised this issue, and it was good to have it raised again. I really do think it's a very important area. And indeed, we need to do some work because there really hasn't been that much adoption in industry. the problem with, it's often said that, for example, microreactors are wonderful because scale up is just numbering up. But of course, when you number up, you lose economy of scale. So, you have to make a good case for it. It has challenges in terms of, having to consider the whole thing at once, and that's not always possible. Okay. Fortunately, Dr. Burka championed a workshop that the NSF conducted early in fall 2014. It was led by Professor Irapetritu and Baldia. They really looked at the research potential in this area and really identified a number of opportunities where process intensification could really have impact. I'm not sure whether that report is out yet, is it? So I would encourage you to go to the NSF website and take a look at it. I thought it was a really very timely that this topic received some attention. Okay, and I think it's a very productive area for our community because, as I pointed out earlier, it requires integration and it requires a careful look at how you do control. The big data subject we all are aware of. We get inundated with information about that, and certainly characteristics that are described in the public literature as, big data is big data because of the volume of information, the speed at which it is generated, and the variety at which it is generated. And it's generally viewed to be unstructured data. And really, our community loves structure. So perhaps we can take advantage of what's going on in this field and add our ability to structure it. And actually, at this conference, we did have some contributions in this domain. Certainly a very interesting presentation by Professor Zhao from Tsinghua University, where he describes some of the activities that he is doing with the major companies in China that involved really extracting abnormal situation management information from plant data. And I think that's actually a topic that also Professor Cedar attacked a few years back. But it needs more effort than just a couple of Lone Rangers. So I think it's an important area. We've also had a number of contributions in the order of 4 or 5 papers that worked on the notion of using ontologies, essentially to create a framework that allows data to be better structured and then searchable.